Now we are connected and recording, streaming. There we go. Okay. So yes, we are streaming. Good. Okay. All right. So this is actually from the final exam of last semester, but that's because of the changing of the order of things, and also because last semester we spent more time to talk about the instructions. Yep.
Is the final exam cumulative?
The final exam is cumulative.
Okay.
In this class. Yep. Okay, so this is one of the questions in the final exam, and it's the form of the question that is kind of important to us. So basically you have to implement isDigit as a subroutine, but using all the standards that we use in this class. In other words, you have to remember, how do we put the parameters on the stack? How do we return the value? How we use the stack pointer, and so on. Okay. In other words, this is it's a simpler version of your homework assignment. Okay. So you look at this and go, okay, how do you do this? It's a subroutine. It's basically just confirming whether the parameter x is a digit or not. Is it a 0 to 9, or is it something else? So how do you do this in the assembly language that we are dealing with? Okay, so we'll focus on this, and the good thing about this kind of question is I don't really need to have a document camera, because it is actually easier for me to type the answer here.
These are unsigned, right? Or are they
huh?
It's not unsigned.
It's signed. Characters are considered signed, so they are integers, or they are.
Actually, it doesn't matter in this case.
Okay, so how do you do this? You have to write the subroutine first, right? And I give you some additional information. The ASCII code of digit 0 is 48. The ASCII code of the digit 9 is 57 in decimal, because the assembler can only take in numbers specified in decimal but not in hexadecimal or in any other form. Okay. All right. So let's go ahead and implement this. IsDigit, as an entry point, needs its own label. Okay. And depending on how you want to kind of keep track of stuff. Okay. I personally like to keep track of stuff like I know x is on the stack, and then the return address is on the stack, and the stack pointer register D is pointing to the return address at the entry point of the subroutine. Is that okay? Yep. Go ahead.
I was about to say, well, we do know the ASCII values from 0 to 9, right?
Mm-hmm.
That's what's given. I would think that x, or whatever value you're storing, x, you're going to be comparing it, well, obviously, you're comparing it to the ASCII values between 0 and 9. I feel like the ASCII values are going to be in a stack, and then you're going to be comparing x, right? That's essentially what you're doing. If you get 0.
Yep. So the question is, how do you get back to x? We don't want to pop D. We don't want to increment D, because remember, everything below where the stack pointer points to can be modified. Okay, so it's not safe to change it. So we don't want to modify D. So the first thing we want to do is to do a CPR. So we copy register D to register C. So C equals D, and so C points to the return address, and then we increment it to C. So the C will now point to X, which means C is not the value of X, C is the address of X. Okay?
LDI, C to C.
And then we can do LDI, C to C, LD, CC, C will work, so C is now the value of X. Okay? Then we can use any, go ahead.
Question. So when we're answering this, we can use like a scratch paper, right?
Yeah.
And so pretty much we can do like the stuff that we're doing on the right. Cause I like to program assembly by doing the comments. It's okay if we do that as well. Like,
oh yeah, absolutely. So we will load C from indirect C, so that C is now the value of parameter X, and then we can do some compare. So now we do LDI. There's no way to avoid this one, because LDI is the only way for me to load something into a register and then compare. So we'll first get a 49, right? So we load LDI. We can choose register A or B in this case. Okay, either one of those will work. So I'm just going to pick A, 48. So now A is the ASCII code of 0. Okay, and then we have to do a compare. Now we know the compare is going to involve register C, which is X, and A, but we kind of want to think about how to kind of order that so that we can, it's convenient to do the conditional branch. And the convenient way turns out to be the obvious way in this particular case. So if we compare CA like this, okay, then we are basically performing a subtraction of C, which is X, minus the ASCII code of 0. Okay, it's the actual subtraction, but we are not storing the result of the subtraction anywhere, so we are just performing the subtraction. So now we need a J blah blah I, J something I, to else, okay, to the else case. So else is here. So now the question is, what do I put here? Nope, not 0, because we perform the then branch when X is greater than or equal to the ASCII code of 0. But we are now specifying less than, okay, but it is signed.
So we borrow, but
No, signed, it means we do not use borrow.
right.
We use the other flag that indicates less than. Which one is that? The L flag, very good. Okay, so we use the L flag here, not the sign flag. Okay, the sign flag can get half the job done, but not always. Okay, so we need the L flag to go to else. Okay, so if we don't go to else, that means we just have to specify a return value of 1, right? That's pretty easy. And then we can now continue JMPI to end if. And end if is a label here. So the else branch is pretty easy too. We just have to put a value of 0 into A. So at end if, we are going to have to perform the actual return operation, which means we do a LD to B. This time you cannot use register A. You have to use either B or C with D here. So B is now the return address. And then we increment D so that we deallocate the space used up by the return address. And then we just have a JMPB. That will be the end of it.
But the question asks if it's also less than 9, greater than 9, right? So
Oh, right. Okay, I forgot about that. So I'm not gonna get full credit for this. Okay, so I forgot the other one. Okay, so we have.
How many points would that be, just out of curiosity?
Huh?
How many points would that be out of curiosity?
I think they all have the same point values.
Less or equal to 9.
You mean for the whole exam?
No, just for the
Really
question.
question there. If
Like
you
how much
turned
out
it
of-
in as you did.
Say
Oh,
it's 4 points,
okay.
How much would you give for that answer?
Well, since I got the first part done and I got the stack stuff done correctly, so this is kind of considered fairly minor. So I might get a C, for the conditional branch implementation, but I would get an A for how to use the stack, an A of accessing the parameter, an A for ending or returning to the caller. So overall speaking, this will be A minus, type of grade.
Okay. Alright.
Yep. So the next one is to LDIA with 57, and this time to compare, I'm gonna let's see. So we are looking for X is less than or equal to 9, which also means if 9, the ASCII code of 9 is less than the value of X, I am branching. So JLI to else, and we're done. Yep.
No, never mind.
Yep. Go ahead.
So you don't check every value between the characters 0 or 48 and 57. You don't have to check every.
Correct.
Okay.
That would be very tedious.
Right.
Oh, I thought of a loop to do it.
Oh, no. I give you this code. You just have to translate the actual, literally translate the C code. Yep. Oh, definitely not use a loop.
Yeah.
Yep.
Could I, after the first one, can I have the JLI? Actually, never mind. I'll probably use this method.
I mean, there are alternatives, but this
Yeah.
is the shortest way to do it.
I like this.
Okay. So is that good? All right. Pretty sure we're recording and with the sound too, so the sound is good. So we're good. Shall we move on? Good. Question number 2 is decompiling. Okay, so we have to decompile or reverse engineer the following code back into C. There are 2 subroutines. Main is a subroutine, sub1 is also a subroutine. Be sure to include as much information as possible. Be sure to use structured code, which means, if you can convert something back into a while loop, convert it back into a while loop. If you can convert it back into if then else, convert it back into if then else. Infer as much type information like signed versus unsigned, that sort of thing. Is it a pointer? Is it not a pointer? As much as possible. Also do the same thing with the type of the return value and also the types of the parameters. If there are parameters or local variables, you can name those in whatever way that is syntactically correct. Because you don't know the application, so there's no way you can actually see, oh, this is a counter, this one is an index, and this one is, whatnot, okay? You can just name those generically like X, Y, Z, okay? So as long as those names are used consistently to represent the logic, it's fine. Is that okay? So we try to do this? Okay. All right. So this is also one of those things where if my document camera is up and running, it would be very, very helpful. So let's see. Did I start it in a different window? Come on. Nope, not here. So we'll go ahead and try it one more time. It sees the device that it is communicating, but it refuses to display the actual content on the screen like this. Which I have no idea why. Because I can see, when I click this, stuff happens on my screen. So it is actually communicating correctly, but it is not.
Maybe you've unlocked the dark mode. Maybe you unlocked the hidden dark mode.
It is. Yeah, so this part is not working, which is kind of disappointing. Okay, let me close this, unplug, plug it back in. We'll try the typical engineering approach. And then we'll try to connect again.
From my childhood, the typical engineering approach involves hitting it with a wrench.
That may not work very well with a tablet. Okay, I'm gonna go back to the debug or the developer option and make it forget. The authorization.
It was working fine in the other computers, so maybe it's just thinking maybe there's something slightly different with this computer. So
it was working in 440. Same setup. Same setup, same kind of.
Maybe there's a slight hardware difference and it doesn't realize it.
You mean the computer itself?
Yeah.
That's possible. But it's a software issue. It's not a
True.
It's not a hardware issue because I can see how. Okay. All right. Click OK. It says check your Android device and click allow USB debugging, and I just click yes. And it's still not displaying the content. So this part is just baffling to me. It's like, why is it not doing it?
Like, I kind of have to wonder if it's expecting the other computer, but it's plugged in.
Okay. Nothing. Still nothing. Huh. Okay, the connected device is unable to access data, reconnect the USB cable and try again. Android file transfer or Samsung Smart Switch must be installed on these devices, but I'm not using Mac OS 10. But that's a cricket. A real bug.
I love when you call it out, it stops. Probably looks around. What?
I'm going to debug it. Slow charging, that's not an issue for sure. Okay, tab.
Of course, we all know the story about how a bug came to be, right?
Yep. Okay, come on.
The first bug was.
Darn it. It can even rotate my screen. Yep. My screen is now rotated. But it just won't work. It won't show the content. So I know the connection there's a connection. It's just not doing it. It's just not the back button works too. Yep. Okay. I'm not gonna wrestle with this for now. We'll try to find the reason why I want to do it that way is because I want to kind of point out, which line is which line doing what. Doing it this way is possible. It's just a little bit harder. So I'll try another way to do this. And the other way to do this is to use a spreadsheet. Okay, so here's a spreadsheet with everything. All right, so what we want to do is to try to figure out what we can recognize easily. Okay, when you're reconstructing a program, you are working from the bottom up. Okay, this is quite contrary to what you're taught in many other classes, which is top down. This is bottom up. Okay, you basically scan through this code and say, okay, do I recognize this kind of thing? Do I recognize that kind of thing? And so on. All right, so out of this whole thing, what do we recognize? This is the end of a subroutine, which is usually where you find certain things, right?
Jump B. So where's B?
Do you recognize these three instructions? We're loading what the stack pointer points to into a register B. We increment the stack pointer, and then we jump based on the register. That's your return. Okay, so we'll go ahead and just do this. Okay, format, merge cells, and say that these three instructions together is our return. I do not have the death stare of Darth Vader, despite common belief. All right, so we know this is a return, so that's cool. This is the entry point of sub 1, right? Okay, and from here we are copying register D to B, and what we know at this point is B is going to point to the return address. Now this you can assume right away because we know at the entry point of a subroutine, any subroutine, the stack pointer points to the return address. Okay, so the moment we make a copy, go like, okay, B is now pointing to the return address. So now B is pointing to some kind of parameter, but it's going to be the first parameter. Okay, and so from this we gather that we have at least one parameter to this function sub 1. Okay, which is kind of helpful. And from here, we are loading A is now param 1 because we are dereferencing B. And now we can say, oh, that's another parameter because we're incrementing B one more time. And then we do another dereference. So B is now parameter 2. Okay, so we got two parameters. A is parameter 1, B is parameter 2, and we're doing a subtraction. So now we can say register A is let's see, A has param 1, so we are param 1 minus param 2. Is that okay?
Yep.
So from this, we can basically gather that the subroutine returns some kind of value. It returns an 8-bit integer. This is sub 1, It has got two parameters. Okay, we'll call this param1, and it has got param2 like that. Is that okay?
How do we know it's 8-bit?
We know it's 8-bit because we are only using a single byte here, and then we are subtracting the 2 bytes because the processor, the toy processor itself, has byte-wide registers.
So if we said just in sub1, in param1, in param2, that'd be incorrect?
It would be okay. Yep. If you say unsigned, it would still be okay because we don't know whether it's signed or not. Whether it's signed or not uses the same subtract instruction. The only time you can tell whether something is signed or unsigned is when you have conditional branches. If you have a JCI, it is unsigned. If you have a JLI, it is signed. So those are the only times you can tell, is it signed or unsigned? Well, since we don't have any conditional branches like that here, we cannot tell. We simply cannot tell. Okay. All right, so that is all good. And since also register A specifies the return value, right? So we know the return value is just param1 minus param2. So we have return param1 minus param2. And we just put an open curly brace here. Put a close curly brace here. That's our sub1. Is that okay? But do you see how I reverse the whole process? Okay. So now we go back to main. Now main is actually more complex. Okay, main has got lots of stuff here. Okay, so we want to analyze main. This one is just for initialize, the stack pointer. Okay, no big deal. We allocate a byte. Okay. Now when you allocate a byte, and you can see that we are not initializing it right after the decrement, there's a pretty good chance this is a local variable. It doesn't make sense that this is a parameter, because with any type of parameter, right after you reserve the space for the parameter, you want to stick a particular value to what the stack pointer points to, right? Why would you pass a parameter to a subroutine where the parameter is just whatever? It doesn't make sense. So this allocate byte, you can basically say this byte belongs to a local variable. Okay, we know almost that for sure. This one is another allocate byte, okay, but we don't know whether it's a local variable or not. The reason why we do not know whether it's a local variable is because we stick a value of 4 directly into it right at that point. So we're gonna call the first one an actual parameter. I mean, an actual local variable. We'll give it the name of x here. Okay. This one we don't know. Okay, but we can say one thing for sure. We are pushing a value of 4 on stack because we initialize the stack. We initialize a register B to 4, and then we allocate the byte, and then we store it on the stack. And then we have another decrement D. Okay. And then we have another decrement B. So when we do this, we're pushing 3 on stack. Okay? Is that okay? Yep.
Why do we have 2 decrement Ds again?
You mean at the beginning?
Yeah, at the beginning.
The first one is to allocate for a local variable. The second one seems to me is a parameter, but I cannot make a conclusion yet.
Okay.
So all I can conclude is these 3 instructions together is a push 4. Okay. So a better way to represent this is to merge these cells. Okay. This is one thing that I can really easily do with a spreadsheet, is kind of to look at all of these instructions and kind of combine these so that we can look at these instructions as a higher level operation. Okay, so we decrement D again, we allocate a byte, we decrement B again, and then we store that. So now these 3 together is push 2. So we insert, format, merge cells, this is push 2. Alright? And then here, this is another thing that you probably recognize is we have some kind of a label, we stick that label into a register, and then we push it on stack. Is that okay? So we look at these instructions here, and we are pushing the return address, and then we're continuing execution in a subroutine. So with these 5 instructions together, we're basically just calling sub1. Okay, so we combine these 5 and say this is the same thing as calling sub1, and then we are deallocating the 2 parameters. So this is also a good indicator that sub1 has 2 bytes of parameters because we're deallocating those. So we just say this is for cleaning up the stack. And then here we have another decrement, and then we store A into D. So we are basically, remember the special purpose of register A is it stores the return value of a subroutine. And we know the subroutine has a return value because of this. Is that okay? So right here, I'm going to combine these 2 because they're performing one particular function. So we are basically pushing the result of sub1 back on the stack. And then from here to here, we have another call. This is a separate call, but to the same subroutine, which is sub1. Okay, combine these. And say this is another call to sub1. We'll analyze what is being passed around, later on, but right now we are just looking at all of these things and just try to do kind of perform what we need to do in a bottom-up way. So merge these 2, deallocate parameters. Okay, there we go. And then this one seems to be storing something into register D. Okay, this is storing. So we're gonna say store return value to something, and then we have the last return 0 in main. Okay. So now we look back at this thing and go like, okay, so we have a pretty good idea of with this sub here, it is using 2 as the first parameter and using this 3 as a second parameter. In other words, I look into a call and then look into what is on the stack for this call. Now I know we have more stuff on the stack, but those other items are not useful to analyze what is being passed here.
That's the next subroutine.
That's the next subroutine, and I'll deal with that later. Okay, so I look at these 3 and go like, okay, now we can combine all of these cells and say this is sub1, 2, 3. What is that for? Don't worry about it. Okay, deal with it later. What is that extra thing here? Worry about that later. Is that okay? Okay, so if that is calling sub1 and we are pushing the result of sub1 on the stack again before we call another sub1, so that means now we can combine everything up to here and basically say that this is the outer call of sub1. The first parameter is the result of the inner call of sub1. But then we still have a 4 as a leftover on stack. This 4 is still a leftover. Okay? So we know we have a nested call to sub1 in that particular way. Okay? Which has its own return value. At this point, I don't know what we're doing with that return value until this part here. So this part is saying, okay, we're taking the return value of the outer sub1 call and putting it into something on stack. So when you analyze how we use the stack, whatever we allocate here is never utilized in one of the calls. Okay, the 4 is utilized in the outer call. The 2, 3 are used in the inner call, but the 1 byte that we reserved at the beginning was not really used. So that suggests that this store is really doing this. We're basically storing to the local variable x here, which means the next increment x here is to deallocate our local variable x, which has no corresponding C code to do it, because C just does it automatically. We don't have to worry about it. So that means, when I have the final version of main, okay, main is technically returning an integer, even though it's not really useful in our case. And then we have a local variable x here. And then down here we have the rest of the code, which is x is sub1, sub 1, 2, 3, and then a 4, and then we return a 0 at the end of main. Okay, so getting to this one, I'm using column F, as the finished product, and then we got a return 0 here, and curly brace. So that's the answer. Is that okay or not?
Okay.
Okay?
Would
Cool.
we need the subroutine out there on column F as well?
So say it one more time.
Would we need the subroutine on column F as well?
Yeah, I think
No.
you wrote it there already.
Yeah, I wrote it here so I
It's
can,
already-
as long as I can find it. Yeah, so basically the technique is you're analyzing the code from the bottom up. You look at things that are indicative of things. Branches are always useful, okay? Because branching is either indicative of a call or a conditional statement or a loop of some kind, okay? So depending on what kind of branching we're dealing with. Now, if you have a branch like this one that is sandwiched between a label and the loading of the label earlier, it's a call. We're just calling the subroutine. If you see something that is the indication of a conditional statement is you're branching to a later point, but it doesn't branch back to an earlier point. If you see a branch from a later point back to an earlier point, it's a loop. So you basically look at clues like that in order to disassemble a program. Is that okay? The analysis of what is on the stack is actually more difficult because you can't really see that, unless you count and go like, okay, so it might be helpful to draw a map of the stack and go like, okay, this is A, it moves down, this is D, it moves down a little bit, and then we make a copy over here so the C points to the same thing. So it might be helpful to keep track of a map of what is on the stack and which register is pointing to where on the stack, because that determines, are we accessing parameter 1, are we accessing parameter 2, or are we accessing a local variable to the subroutine. So you need to kind of keep track of all of that stuff. The way we do it in class can be helpful. Okay, so you basically have to choose a way so that you can keep track of all of that stuff. Okay, all right, so moving on. I think we are looking at, excuse me, this one here. So this is done. Oh, this is just exam 2. We got this one already, so we can get rid of it. Okay, so that's question 1. We got question 1. We just got question number 2. This is question number 3. Not so pure RISC architectures have opcodes that perform the following operation in pseudo C notation. So we're combining these two. Okay, let me zoom in. Okay. What is that? Don't we do this, a lot of times, or do you think, I have no idea what this is? D, by the way, is register D. What is the first line? Which instruction corresponds to this C code here?
Decrement D.
Decrement D. And then assuming X is a register, what is this doing?
Loading the value.
It's ST. We are storing.
Yeah.
So we are storing to what D points to, the value of a particular register. Don't we do this a lot?
Yes.
Okay. So in the
we have this as a pseudocode in
oh we just
PGP.
we just did it quite a few times, didn't we? Okay, not this one. This is the subroutine, but in the other one. So this is also something that you can, not only for this class, but particularly for this class, is there are only so many ways that I can ask questions, and since all the questions are related to the programming, the microcode, and stuff like that, it is possible that one particular question may supply clues to another question.
Oh,
So when you're stuck with one, move on. Okay, don't try to spend too much time on one, because the moment you move on and you answer the next question, it's like, oh, okay, the answer to the first question is actually a part of the second question. Okay, go back, finish that one.
they do that all the time.
But if you're really like, if you insist to answer the questions in a specific order, you might get stuck with one and not realize that a clue to answer the earlier question is in a later question.
Well, it's just good test taking strategies in general. You should always skip the ones that give you trouble. It also builds up confidence, gets your
Right, but you
mind
don't want to
thinking
skip
about the just
too
subject forward.
quickly. Yeah, so you basically use a
Right.
timer. Just keep track of. Okay, I'm supposed to answer these questions. Set a time. Every 15 minutes. I'm supposed to move on to the next one, so that at least I have enough time to touch every single question and give me some time for each question. So you just look at your clock. It's like, okay, it's 12:45. I'm supposed to be on the third question, and I'm still on the second one. Move on. Instead of going, I'm close, I'm almost done. Yep, just move on. So that's what I would do, if I'm taking an exam.
I noticed with the last test that we did, I tend to jump around a lot. I went from the first one, second one, third one, fourth one, fifth one, all in the space of 20 minutes, and then I went back.
Yeah.
And so I do part of the first one, move on to the next.
Yep. If
part
that's
at a time.
if your brain works, efficiently this way, do it this way. Some people are more focused and they just you need to like, get one done first before they move on, and the other people are more,
Your brain's
okay.
still working on it when you move on too.
Exactly, because I think your consciousness is really about kind of like an iceberg. What you see above the water is your consciousness, and then what is below is the bulk of your processing power. So if you try to use just the tip of the iceberg to do all the work, it's not going to get it done. After all, the Titanic was not sunk by the tip of the iceberg. It's what's under the water that sunk the Titanic. It's not what is above the water.
Cheery analogy.
Yes.
All right.
Okay, so in this case, so D means register D. X specifies one of the four registers, which can potentially be X itself. Assuming the opcode pattern is blah 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 for this family of instructions. So once again, this XX refers to this X here because we need 2 bits to specify one of 4 registers. So we are basically looking at in hexadecimal. Okay, this is bad because it is supposed to be in binary. Okay, binary. So this is 2, and this is either 0, 1, 2, or 3. Figure out the start location of each individual opcode in microcode ROM and specify the bit fields of each microcode slice. Okay. In a field, if a field depends on X, specifies X. If a field can be 0 or 1, specify a question mark. A 0 means a field must be a 0. A 1 means a field must be a 1. A 0 or 1 in place of a question mark does not receive credit. In other words, if a particular bit really does not make any difference, tell me it doesn't make any difference. Is that okay? All right. Yep, go ahead.
So I didn't know what you meant by stealing. We talked about it earlier in class. If we don't understand the question, would you have answered that question if I came up to you during the exam?
Yeah, you can just come up and ask me.
What do you mean by stealing? Can you explain that?
We are basically using the same binary opcode to implement a different instruction.
If I did understand it right.
Yeah, just come on up and I will try to clarify. Yeah. Okay, so we need to specify the start location. All right. We're dealing with a family of instructions, so the start location depends on which one of this family. So the way to do this is to specify this is 0x20. Now, 0x2, the 2 comes from the most significant 4 bits being 0010, and this 0 comes from basically these 2 zeros here, because XX can be 00, okay? And then we say plus X. X specifies which register we're dealing with. So X itself can be 0, 1, 2, or 3, okay, in binary or in in hexadecimal or in decimal. But the start location is not this. The start location is shifted by 4 bits. Remember the 0 that we pad in as the least significant 4 bits of the microcode pointer. Okay, so this is specifying the start location. In the first slice, we want to implement this. Now, if you want to implement this, you can just copy and paste. If you have the decrement instruction, slide all the slices for the decrement instruction in front of you, copy those. There's no need to reinvent the wheel, okay? So, you know, if I remember, okay, it's a 0 here, it's a 1 here. We're not changing the program enable. Now, but you have to be careful, because if you encounter something that can be either a 0 or 1, you have to make sure you use a question mark, okay? So we have to make sure this one is a 0, but then PC mux is now a 0, is a question mark. Is that making any sense? If you're not enabling the program counter, the mechanism that specifies how you update the program counter, they become irrelevant. If they're irrelevant, you put a question mark. You basically say, you can specify a 0 here, fine. You can specify 3 here, you can specify 7 here. It doesn't make a difference, because the program counter is not enabled. It is not going to update. Doesn't matter how you specify the rest. Are we accessing RAM? We are not accessing RAM. We are really just, the first slice is just decrementing the register. Decrementing a register does not need to use RAM at all. So this one seems to be like, maybe it doesn't matter, okay? But remember, oh, this one actually doesn't matter. Okay, so we'll put a question mark here. Are we using the ALU? The operation we are focused on right now is decreasing the register D by 1. Do we need the ALU? Yep, we definitely do. So EN has to be a 1. But since it's a decrement, do you guys remember which out of the ordering of all the things that we can do with the ALU, which one is a subtraction? 0 is addition. Yep. 1 is the subtraction. All right. Do we need to specify our register output 1 demux? It is important. Which way should it go? You can use a, you know, if you have a processor, you know, thing here, you know, that would be helpful. I think this one needs to be a 0. Okay. Okay, I'm gonna put a question mark here. You know, we can come back and revisit later. But which one we choose is actually not important. Because remember, the whole point is we are using a constant to supply to into of the ALU, which normally is connected to register output 1. So it doesn't really matter which one you select. It doesn't really matter because it's not connecting to the ALU. This one is kind of important. Which how do we connect register output 0 to the ALU? Of course, I cannot remember which one it is, so I'm gonna cheat and read my own code. Pretending that this is, you know, something that I brought to the exam. So I would vim processor opcodes. We are dealing with decrement, right? Decrement.c. And let's see. Okay, we are looking at register output 0 mx, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is supposed to be a 1. Okay, this one is important too because we have to say which register serves as register output 0 of the register bank. Put an X here. Because whichever variant instruction you're implementing that specifies this X, that would be the same X that you need to put here. Nope, I take it back. I'm wrong. This one has to be a 3. It has to be a 3 because we are subtracting 1 from specifically register D. So it has to be a 3. Okay?
Because if D is 0 to begin with, then subtract 1, it becomes 3.
Because we just want to subtract 1 from D, not the other register.
Yeah.
We're subtracting from the stack pointer. Okay, so register output 1 enable needs to be a 1 because we need to say yes, we are using it. Register input select is going to be register D again, which is a 3. Register input enable needs to be a 1 because we want to update the register D, so that has to be a 1. Register input mux, oh, that one is okay. This is the 1, 2, 3, 4, the 4th entry from the bottom. 1, 2, 3, 4. Okay, that one has to be a 1. I think that one is actually important because there are multiple ways to update the registers, including from RAM, right? So this one is important, has to be a 1. RAM load can be whatever because we are not using it. RAM select has to be a 0 because we have to turn off RAM. It's like, don't pay attention. And then this is huh?
That's why the last one doesn't matter.
Yep. And this one is instruction register enable. We are not changing the instruction register, so this one has to be a 0. Okay, so this is what I mean by certain things have to be a question mark. This one I'm pretty sure is a 0. Okay, next slice. We need 2 slices. The next one needs to implement this. Okay, you go like, but Tech, isn't that the same thing as this? And the answer is yes. So that means you can just copy and paste. Find out what is the slice for this instruction and just copy and paste it here. Okay, so I go back to here and I just go like, okay, we're gonna look at st.c. Okay, so but remember, you cannot just kind of copy and paste. You kind of have to look at all of these and find out which one needs to be a 0, which one can be a question mark. Okay, so you got to differentiate between those two. Okay, so we are storing. Okay, we are not resetting the pointer, microcode pointer. We are definitely incrementing the microcode pointer, so you need a 1 here. We are not changing the program counter. Put a 0 here. And since we're not changing the program counter, how you specify the mux is not important. Put a question mark here. We are indeed using the memory, so address mux is now important. I think a 1 uses PC to specify the address bus, and a 0 uses a register to specify the address bus. Okay, I can always just bring that up, right? 2000. Okay. So using a picture is fine. Using the code itself is fine too. So I just want to find out what happens to this particular mux here, and I want register D to drive it. So that means I want this connection, which means address mux has to be a 0. Okay, so I stand corrected. This one needs to be a 0. We are not using the ALU, so ALU op is not going to be important, and we have to make sure that we turn off the ALU. Register output 1 is important, okay, because we need to know which register. We need to connect the output 1 of the register bank to the address bus. Okay, so that means this particular demux has to specify a 0. This one has to be specified 0. So when we put our answer here, this one has to be a 0. It is register D that is driving the address bus, so this one has to be a 3 to specify register D.
Right.
Register output 0 is not used because we are, nope, I take it back, it is useful. Okay, so we're using a register to specify what to store in RAM, so register output 0 is indeed useful. So this output is important, and that's why this demux is useful too. We want this demux to specify the address bus. Okay, here's the address bus, highlight it, and we can see it goes into here, which is output 2 of this demux, which also means register output 0 demux has to be 2. This is where X goes, because we're using register X to drive output 0 of the register bank. Okay. Register output register output 0 enable. Obviously, it is important because otherwise we wouldn't be specifying these values earlier. Register input select is not important. We are not updating a register. We are updating a memory location, but not a register. So that is not important. Register input enable has to be a 0 because otherwise it will update one of the registers, which is not what we want. This one becomes unimportant because, hey, it only controls the source of updating a register in the register bank. Since we're not updating a register, it becomes useless. RAM load needs to be specified. We are specifying a write operation, so this has to be a 0. And RAM select has to be a 1 because now we're performing operations to the RAM. Instruction register enable can still be a 0 because we are not loading another opcode in, so that has to be a 0. Whew. Okay. So if you answer this question with this, you get full credit, even though we don't have the last instruction. The last slice, technically speaking, is 1 followed by all zeros, but they're not exactly all zeros in this sense because we have to say, okay, which ones are real zeros and which ones are question marks.
So we can just leave it blank.
You can just leave it blank, because I'm most concerned about these two slices. Yep. So is that okay? This is why I told people earlier to prepare your own thing. It's like, oh, this is how subtract works, this is how add works, this is how compare works, and so on.
And then using the tab as well.
Yep, because you can just look at this whole thing, go like, oh, okay. Okay, so question number 4 is again implementing something, and question number 5 is to decompile again. So the type of questions is basically just the same type. Okay, so let's look at this one. How would you do this?
2 parameters and put a third register, initialize it to 0, and it's check to see if.
Well, let's go ahead and do this. Okay, sub 1, and this time we got K and return address, and we know the stack pointer points to the return address. So this is what the stack looks like at the entry point of the subroutine. So we do a CPR CD. So C is pointing to the return address. Increment C. So the C points to N. And then we increment C again. So the C points to K. So because this is a disjunction, it has to be evaluated from left to right. So we cannot flip the order and go like, hey, we get to N already, might as well do N first. Nope, cannot do that because of the enforcement of left to right evaluation in a disjunction. Any logical operator is like that. Okay, oops, sorry, click on the wrong part. Okay, right there. Okay, there we go. Alright, so the next thing we do is do an LD. I don't want to destroy C because it's useful later on.
Make B 0.
Yeah, we can do an A first, So the A is K. And then B 0. B is actually 0. And this time we're really just checking for equality, so the compared order of the compare does not really matter. Okay. Unfortunately, we only have JZ. Okay. So JZI is going to go to the then case, right? Okay, because we have a match. Okay, so we confirm that K equals to 0 in this case, so we have to go to the then branch. Okay, so we stick a then branch here, and then we decrement C, so the C points to N again, Yep, load it to A. So the A is N. And then the same kind of compare, AB. And then do a JCI to then again. Because this time we confirm that N equals to 0. Time to go to the then branch. If we do not, then we go to the else branch. At the then branch, we return a 0. Okay, LDI A0, we are done. And jump all the way to the end. So don't forget to jump all the way to the end of the conditional statement if you have an if then else structure, because otherwise it would just fall through and execute the else branch right after the then branch, which is not what we want. So we have to go to end if. So end if is going to be here, and now we can specify the else branch. The else branch is returning the recursive call return value plus k. Okay, so how do we do this?
Yeah.
Eh.
Right.
So let's see. So we need to go. So we're gonna need to.
I would do the recursive call first. Okay, so let's go do the recursive call first. There are several ways to do it. Okay, we have to get the k regardless. Okay, so we got to get the k. So let's go ahead and get the k. We know at this point that C points to N. We don't. Actually, we do not know. Do we?
Oh, we don't know.
No, we do. Actually, we do.
Yeah, C's still putting it.
But
Oh, yeah.
if you're not sure, okay, if you're not sure, don't waste your time, okay? Because
Just load D.
yeah, because
Yeah.
this is cheap and it is always correct. I'm not gonna grade based on efficiency of your code, okay? So if you are saying, okay, I can't really keep track of C whether it's still pointing to K or N at this point, just reload it, okay? It's no big deal. So it goes to the return address again, increment. So now C points to N, okay, which is not what we want yet. Increment C, so C now points to K. Is that okay? All right. So we do LD, okay. Oops, there we go. So A is K. All right. So now we have a little trick that I can do here. I need K in two cases, right? I need K for the immediate call that I'm trying to do, but I'll need K again when I come back and add it to K. When we come back, I cannot make any assumptions of the registers anymore because supposedly when you call a subroutine, all the registers got messed up, right? So since I have K here already and I don't want to waste the time to recompute K, I can now save it on the stack. Okay, so I can decrement D std A. Okay, so we save K, but we're gonna do it one more time. Decrement D std A, but this time it is the second param to sub1. It is the second parameter to the recursive call. Then we have to find out what is N. Since we know K, or since we have the address to K, we can decrement C. So the C points to N again. And then we do a LD. We can use A again, because register A is not useful anymore. So now A is N. Decrement A. Decrement D. Okay. Just to be specifying what this is N minus 1 stda push N minus 1 on the stack. Is that okay? Which is our first param. Once this is all done, we call the subroutine, which is LDI sub1 return address. Sub1 return address is here. Okay. Decrement D. Oops, forgot to specify which register gets it. Nope, wrong register. stda. So this is pushing the return address on the stack. Then we need an unconditional branch, the subroutine, which is sub1. When we are back here, we need to clean up the stack first, okay? So we need to do an increment D twice to clean up the stack. Clean up parameters. But then now we got two things that are important. Register A has the return value, which is what we want, and then K is on the stack. So now we can say pop it. Okay, we can just do LDB indirect with with the stack pointer. So the B is now K again. So this is a nifty little trick because earlier when I had the value, I push it twice on the stack. So this save is utilized here. But once I utilize, I have to remember to say, nope, it is now useless, and now we can perform the addition. This part is in register A, this part is in register B. Okay, so we just say add AB. Okay, this is specifying the return value of sub1 plus K, and we're done. We have just specified the return value. So now we can go to endif because this is where the two branches merge. Each branch will specify the return value but not actually perform the return back to the caller operation. So this is where we need to specify the return to the caller type of operation, where it starts with the LD instruction.
Wait, wouldn't we at the end of sub1 return address, when we need to label a call jump back into in case
We called.
okay.
This is the recursive call. So this is the call itself,
Yeah.
and we set up the parameters, but this is for cleaning up the parameter of that call.
Okay.
This is retrieving K from the stack. Okay, I have to highlight two lines. This is retrieving K from the stack. This is actually specifying the return value. And then when we fall through here, it is time to just do the return, which is retrieving the B is the return address. Now we can do an increment D to deallocate the return address, and then JMPB. That's the implementation. Okay.
Recursion gets me sometimes. The stack's not so hard.
Recursion is no different from calling any other subroutine. The fact that you're calling the subroutine that you're currently in really has no implication to how we implement the call itself.
Yeah, it's hard for me to think around subroutines for some reason.
Aha. Okay. It's okay. So when you think about subroutines, the most important part is the agreement between the caller and the callee. They agree on what? Well, they agree on several things. One, the parameters are on stack. They are in locations higher than the return address. The last parameter has the highest address. The first parameter has the lowest address. And then we have the return address right below the first parameter. And then part of the agreement is the stack pointer always points to the return address at the entry point of a subroutine. The subroutine can modify any register except for register D. When we return from a subroutine, the subroutine is responsible to deallocate the return address. If the subroutine has any type of return value, it is in register A.
Okay.
So all of those are the agreements between the caller and the callee. And as long as those agreements are met, then anyone can call anyone else, including yourself, including the subroutine that you're already in.
Okay.
Okay? All right, so let's look at this last decompile. Okay, this decompile doesn't have a main, so that means you don't have to deal with main. So we'll go ahead and do the same thing. Copy, put it into a spreadsheet. Okay, so we can use the same one here. I can use a separate sheet. Paste. Okay, there we go. All right, so with any type of chunk of code, the first thing I would do is to go to the end. Okay, because these three are easy to recognize. We are loading something from the stack pointer to register B. We increment the stack pointer, but then we branch based on the register. These are the easiest to recognize because it is just a return to caller kind of return. If there's a load to register A right before, we have some kind of return value. Okay, so you can just say return value is something, but we don't know what it is, but there's a return value. Is that okay? Because otherwise I wouldn't waste my time to copy something into register A right before I return from a subroutine. Okay, so now we go back to the beginning. Go like, okay, so let's figure out what is happening here. So now we know that A is pointing to the return address. Okay, after this, A points to the first parameter. We don't know what the first parameter is, but right now we know that B is the first parameter. Okay, because we dereference A and A points to the first parameter. We keep going, so that's probably a second parameter, and then B is the second parameter. Is that okay?
Yeah.
So we know sub1 has two parameters. So we know at this point that sub1 has param1 and param2. Not quite sure about the type of the two parameters, nor the type of the return value, but we know that it has a return value. We just don't know what the types are. So here's L1, and right here it tells me we have a loop. Because I haven't seen any jumps to L1, which means any use of this L1 is after the definition of L1 itself. That's the indication that we have a loop. Okay?
Because there'd be no point for that label to be there in the first place.
Exactly. So we have a loop, and it is confirmed by this jump instruction here. When you see this particular structure, a unconditional branch back to an earlier point, it is highly likely this is a while loop. Okay?
So while.
So we know there's a while loop. Okay? We don't know the condition, what the condition is. Okay? But we just stick a question mark here. And then we look at, so if this is a while loop, right after the unconditional branch, there has to be a label too, so that we can mark the point where we exit the loop, right? So now you have to focus on when do we get out of the loop. This is where we get out of the loop. Okay, so how do we get out of the loop? So the way to do this is to analyze what is in A here, okay? So register A is the dereference of parameter 2. Is that okay?
Okay.
Because C is parameter 2, so when you dereference it, A is the dereferenced of param 2. It is what param 2 points to. Oh, okay, that is kind of helpful because now we know param 2 is a pointer. We don't know quite what a pointer to, but it is a pointer. Then we perform a store to whatever B points to. Okay, so that means we are dereferencing pointer 1, a parameter 1, and then we put A into it. Or to be more exact, if you forget about A, this is what we're doing. So we know parameter 1 is a pointer 2. So you can see how I kind of go back and forth, which makes it kind of difficult when you do it on paper. So when you do it on the paper, you just kind of use like an insert mark and just use arrows and help you attach additional stuff. Okay, now this is before we stole the opcode of AND AA for something else. So AND AA really means AND AA, which is really just checking is A null or not. Okay, it's comparing A to 0.
Oh, okay.
Yeah, so if it is 0, if A is in fact 0, we branch. So this is basically saying, if param1 equals param2, if this whole thing is 0, branch exit loop. Because we know L2 marks the exit point of the loop here. Which also means we know how to stay in the loop. Because if this is saying how we exit the loop, it is also saying if this is not equal to 0, stay in loop. Is that okay?
So while A is greater than 0, the
Yep.
loop continues.
Exactly. So now we can go back here, change this question mark to param1 equals to param2, stay in loop. That's our stay in loop condition. This part here corresponds to the body of the loop. Okay, this is the actual body of the loop.
Wouldn't it be equals equals?
Huh?
Wouldn't it be equals equals in a while loop?
You mean this one?
Yeah.
Nope, it isn't equal because we are actually doing the assignment. We are
Okay.
we are copying while comparing. So if you want to avoid, if you want to make it less confusing, you can specify it like that.
So-
Same. It doesn't really change the meaning, but it is more clear. Incrementing B means param1 is incrementing, and this is incrementing parameter 2. That's the whole thing.
Is it
Almost.
incrementing actually the parameter, or is it incrementing the address?
It is incrementing the register that is serving the purpose of the parameter.
Okay.
Because we are
'Cause you already
equating
have content there.
we're equating register B with param1, and we're equating register C with param2.
Okay.
So because of the way we set it up here, when we increment B, because these two registers were not modified or used in anywhere else, so we know that these two are still param1 and param2.
Right. Okay.
So after we get out of the loop, we copy A to D. So we have a few more things to do, right? So we say, at this point, A points to the return address. At this point, A points to param1. So, okay. So that means the return value is really just param1 because we dereferenced the address of param1 and put it back into A. So when we combine all of this stuff, then we can basically say whatever the type of param1 is also the type of the subroutine itself. So okay, that's what we know from combining all of the stuff that we have done. This is the while loop. So while param1 equals to the reference param2, as long as this is non-null, do the following. And what we are doing in the following is just incrementing param1. Oops, doesn't like that.
Because spreadsheets hate.
Okay, fine. That.
They hate mathematical symbols at the beginning.
I just use plus plus. For some reason, plus plus triggers the interpretation of this is an equation.
You have to hit single
Quote.
comma beforehand.
Yeah, single quote.
Yeah, single quote.
Yep, and then here we combine all of these to return. So all of these is basically just return param1. That's the end of the whole subroutine.
Okay.
Is that okay? So together, what is this whole thing doing? We have done this. We have seen this already, by the way. It's a string function of some kind. What is it doing? It's changing one of them. So there are only so many string functions that will change one of the parameters. What is this one doing? It's changing, it's copying until we see the null character.
Is it duplicating a string?
It's duplicating a string, and there's a name for that function.
String copy.
String copy. Yep, this is string copy right there.
I never did finish learning to say yeah.
To be fair, that's like a 400 function. You don't learn that until like.
String
like,
compare?
The string function. You know about string compare, but you don't know the.
I should have known
To be
about
fair,
it.
no, that's sorry. We learn about C code and stuff like that later. The C string, sorry.
Yeah, that's 360 stuff.
Not the C string part. It's just the regular string that we were taught there in the book.
Yeah, well, either way, but the stuff that we do here is just dereferencing, adding to a pointer.
This stuff you can figure out.
So whether you can, I'm not asking, which NC function, is corresponding to this code. I'm just saying, okay, disassemble the code.
But just string compare as the answer, would that fly?
No, because you have to tell me what the structure is. Because I can implement string function.
Structure. It has a structure.
No, that's not true. Because I can implement string copy using recursively,
Yeah.
and yet this is not recursive.
No, it's a loop.
Yep. So not quite the same.
Yeah.
All right.
Should still have known it since this is in the book that I've been studying.
Oh, okay.
Well,
Yeah, but that's
I'm
not
doing
needed
home
for this test. Alrighty, I'm gonna stop.